Okay, today we're going to get into something called stoichiometry. You've heard of it before? Okay, stoichiometry is in three parts. One part we're doing today, another part we're doing tomorrow, and next week we're going to put it all together. So today we're going to talk about some conversion factors regarding some chemical characteristics. So I'm going to introduce you to a new unit. Units are all endeavors have units convenient. Whether you're cooking, whether you're doing chemical experiments, physics, engineering, biology, we all have units that are convenient. For example, if you're buying a car, the unit is called each. You buy one at a time unless you're a fleet dealer, but normally you're buying one at a time. So the unit is each. If you're an egg farmer, typically the unit is a dozen. If you're Office Depot and you're selling paper, typically you sell it by the ream, 500 per ream. Now I want you to look at something. As we go down here, notice the items get smaller and the unit gets bigger. Car's big, talking about each. Sheet of paper, talking about 500 a piece. So let's talk about atoms now. Are they small? Yes, you should all be, yes, Ferguson, they're really small, really small. Let me show you how small. Ten to the 23rd. That's a lot of zeros. So that tells you how small the atom is. Atom slash molecule. Molecules are a conglomerate of atoms. Really small stuff. So the convenient unit is going to be mole. And the word mole comes from molecule. Okay. This number, 602 times 10 to the 23rd, a guy named Avogadro discovered it. So it's called Avogadro's number. And it goes out a bunch of places, but I usually round it off to two places. So I think I mentioned this before, but when I was in school, in both high school, undergrad, we had slide rules, no calculators. And the slide rules were 3 sig figs. So I think all the time in 3 sig figs. So 6.02 times 10 to the 23rd is 3 sig figs. You'll notice a lot of my problems, 3 sig figs. I had a special slide rule. It was circular and it was about this big around. And if you took it out, it was about this long, equivalent. So you could go 4 sig figs with it. That was a big deal. Ooh, 4 sig figs. Okay, so if we took, let's look at beryllium. Okay, beryllium has got 4 protons, 4 electrons, 5, on the average, 5 neutrons. Okay, so we're going to be working with the decimal numbers now. So if we took beryllium, standard old beryllium, we mined it, we refined it, and put it on the scale. If we put 901 grams of that on the scale, that's equal to 1 mole. If we counted the atoms of beryllium, it would be, we'd have Avogadro's number of them. 602 times 10 to the 23rd. Okay? So that's what that decimal number really means. And I gave you the definition before. It's the average isotopes occurring naturally, all that stuff. But just being realistic, whenever you go to the store and buy beryllium, you don't buy one particular isotope, you buy a mixture of isotopes. And that's why we go by the 901 number rather than 9, 10, 7, 8, or something, some integer. We're using the average. Okay, so this then leads to some conversion factors. So we're going to have 3 new conversion factors. One is the molar mass. And that's very, very specific to what elements you're working with. Is it one element or many elements in a molecule? If it's one element, we call it atomic mass. If it's many atoms together, it's called molar mass. And of course, it's a fraction. So we have grams per mole or moles per gram. So 2 conversions, we have the inverse. The second conversion factor is Avogadro's number. 602 times 10 to the 23rd atoms or molecules per mole. And you've got the inverse of that. Now, that doesn't matter whether you're talking about ducks, helium, or water molecules. It's a counting number. It's like a dozen. You can have a dozen pencils, a dozen eggs, a dozen cars. It's just a counting number. So think of Avogadro's number as a counting number. So whenever the problem says how many, think Avogadro's number. Think of the molar mass. And then lastly, when we talk about gases, gases are very compressible. We're going to talk a lot about gases. I don't have a whole lecture on gases, but basically, gases are very compressible. And because of that, they occupy the same amount of volume regardless of what the gas is. So if we're looking at gaseous water molecules, 1 mole of them is going to be 22.4 liters. If we're talking about helium atoms, it's going to be 22.4 liters. They're all the same volume-wise. And the reason is the distance between gas molecules and atoms at an atomic level is pretty great. That's why it's compressible. Now, I put this caveat down here called STP. That's short for standard temperature pressure. So the 22.4 only is valid at standard temperature and pressure conditions. So temperature is temperature is 0 degrees, pressure is 1 atmosphere. Now, when you deviate from that, it's no longer 22.4. There's something called the gas law that will tell you what that deviation is. So the variables are P, V, number of moles, and temperature. And I have a whole lecture on that. So and then of course we have the converse, or inverse. 1 mole over 22.4 liters, 22.4 liters over 1 mole. So you've got 6 new conversion factors, really 3, and they're inverses. One does not matter what gas we're talking about. Avogadro's number. It doesn't matter what we're talking about because it's a counting number. However, for molar mass, It's extremely specific. You have to know what atoms you're talking about or what molecules. So that's specific to the chemical. Okay? All right, and then you need a periodic table by your side. Okay, so let's do some problems. And these are all going to be conversion problems. Now, let's go back to our unit 1, 4 steps. Balance the equation. If nothing is happening, there's no equation to balance. What's given, what are we trying to calculate, and what are the conversion factors to go from the given, what we're trying to calculate. Okay, how many grams of water are in 3.4 moles? What's given? And what are we trying to calculate? Grams of water. Now we're going to start putting the chemical above the number, because when we start having a chemical reaction, we have to compensate for what's going on in the reaction. We have to know what's starting and what's changing. Okay, so do we know a conversion factor that has grams and moles in it? Molar mass, grams per mole. Okay, so we've got to cancel the given. Grams on top. So we go to the periodic table. We have to know the formula for water. 2 H's, 1 O. So you look on the periodic table. Oxygen is 1600. Hydrogen is 101. That means a molar mass for water, H2O, we have to add up 2 H's and 1 O. So that's 18.02 grams per mole. Okay, that makes sense? So this is just like unit 1, only we're using chemistry stuff. Now, with molar mass, it's not infinite. It's a measured quantity. So our answer is going to have 2 sig figs. This should look blindingly similar to unit 1.
But 6.1 times 10 to the first.
Or 61. Yeah, let's just do 61 since. And yes.
So if we were to do it into a standard,
Yeah, either way is fine. 6.1 times 10 to the 1 or 61.
and do you also want grams H2O or do you just want grams?
Well, the H2O is up here.
For the mole.
It's up here. Oops, I'm on erase.
But you not want it in the final answer.
That's
Graham.
You can do it either way.
Oh,
Watch, you can put H2O in.
I didn't know.
Oh, absolutely not. That could be clearer, actually. So. Okay. Does this make sense? This should be very, very familiar if you based on unit 1. Okay, so let's look at kind of an opposite problem here, where we're starting with grams and we're going to moles. Okay, so all we're doing this now, there's no chemical reaction. So there's no equation, which we're going to cover tomorrow, chemical equation to balance. And you're going to have a dry lab on balancing equations. And you're going to have 2 labs on reactions. One is called single replacement reactions, a wet lab, good lab, and a double replacement reaction, another good lab. Lots of color changes and all that stuff. Pretty cool. All right, so we're starting with .6, and again, we're using water since we don't have to look up the molar mass for water each time. And we want to end up with moles of water. So we need to always cancel our givens. So grams needs to be in the bottom, moles on top. I'm looking at 3 sig figs, 4 sig figs. Our answer is going to be very straightforward 1-step conversions. Okay, so let's look at this one here. How many molecules in water? How many? Counting. How many? So we're going to use Avogadro's number. How many molecules of water are 2.34 moles of water? We're starting with moles of water. Get to numbers. Avogadro's number. So moles cancels. Since we're working with a molecule, it's going to be molecules. Water to water, so there's no chemical reaction. And we're looking at 3 3 sig figs. So 141 times 10 to the 24th molecules. So that's a nice variety of single step conversions. We're just counting, we're converting them to moles, moles to numbers, moles to grams. We could do the same kind of problem with liters. And we started with 34 liters of gas at STP. How many molecules of water are there in 34.5 liters of gaseous water? Okay, so we've got to cancel a given. Now, can we go directly from liters of water to numbers of water? No, so we got to have an intermediate step. If in doubt, convert to moles. So we're going to use a conversion factor 22.4. Okay, now we're in moles. Now we're going to go from moles to molecules. Sorry, what?
That's 6.
I'm not sure your question.
Yeah, all I got is numbers wrong. The.
Oh, yeah. So in 34.5 liters of water at standard temperature pressure, let's put STP here just to reinforce that. We've got 927 times 10 to the 23rd molecules of water. So we're going to see on most of the problems today, we're going to have to convert to moles as an intermediate, as a base unit, moles. Throughout disciplines, chemistry, everything is per mole, per mole, per mole. Degrees per mole, molecules per mole, always per mole. So that's why it's always if you're in doubt, convert to moles. Engineers, moles. Physicists, moles. It's a very universal quantity. Okay, and it's 3 sig figs all the way across, so I rounded to 9 for 3 sig figs. Um. Okay, we've got interesting problem here. Okay, so we've got how many hydrogen atoms are in 12.5 grams of water? Hydrogen atoms, not molecules, atoms. Okay, so if I've got a bicycle, I have 10 bicycles, how many wheels do I have? 20. There's 2 per bicycle. And you have 10 of them. Right? If I have a mole of bicycles, how many wheels do I have? 2 moles. Remember, because moles are just 602 times 10 to the 23rd, a lot of bicycles. It's kind of like a Chinese kind of description, how many bicycles are, a whole bunch of them. Okay, I want you to keep that thought in mind. Converting from the whole to the parts. Whole bicycle to wheels. Whole to the part. Okay, so first thing we need to do is find out how many molecules of water we've got. How many bicycles we got. From there, we can go to atoms of hydrogen. Okay, so we're starting with 12.5 grams of water. We want to end up with hydrogen atoms. Okay, so first is we're going to do is convert to moles. And then from moles to the number of molecules. Now, the last conversion factor is atoms per molecule, wheels per bicycle. So 2 H's, atoms, for 1 H2O. Now we end up with atoms. Now, frequently, I will give you one of these on a test, test 3. Half of you will miss this problem. Half of you will calculate molecules. I've been giving these problems for decades, and that's typically what happens. So read the problem carefully. So 835 times 10 to the 23rd atoms of hydrogen and the molecules of water. Okay, so does this problem make sense? As far as conversions go, in this part of stoichiometry, this is about as complicated as it gets, this problem here. So if you're comfortable with this problem, good shape. So we went from a 1-stepper, grams to moles, moles to grams, to a 3-stepper down here. Okay, does this problem make sense? let's do this one here. Um. So we want to go from liters at STP of water to number of molecules. Number of molecules using Avogadro's number. Now, I mentioned stoichiometry. This is first part of stoichiometry. You will cover what we're covering the next 3 weeks in 2 lectures in 1A, maybe even 1 lecture. So this unit, again, I want to stress is really important. And as well as unit 3 as well. Those 2 units are extremely important. You will be so far ahead of someone who hasn't had a prep class. That's why we're crying for more prep classes. We don't have bodies to teach them though. We barely have enough bodies to teach the 1A and the 2A classes. And we frequently cancel 2A classes. Just aren't enough of us to go around. Sac City's got the same problem. AR's got the same problem. Even worse up in Nevada City. It's so rural that just can't find people. Okay, this is the essence of your hydrate lab. Copper sulfate is a really pretty crystal, and the pretty version of the crystal is called a hydrate. That means it has water bound up in it. Your objective for doing that hydrate lab is to find out how many waters are bound up in the crystal of copper sulfate. Anhydrous copper sulfate, no water, is this pale blue. The hydrate is a very, very pretty color. It's amazing difference. So this is a typical stoichiometry problem. You can be given grams, I'm going to convert it to moles, and then the next step is to convert chemical equation. You've got to balance it out. And this is where the balancing comes in. So you're looking at how many coppers are on the left, how many coppers are on the right, how many S's are on the left, how many S's are on the right. I call that doing an inventory. Did you get into that when did you get that far? Balancing equations?
And I
Okay, so that's what we're going to be doing tomorrow. We'll be taking, let me show you what a typical stoichiometry problem looks like. All right, 15 grams of water is formed. How many grams of methane are consumed? Now we have a chemical reaction. So step one in our four-step process is balance the chemical equation. So this is the equation here. CH4 is methane, O2 is oxygen, yields water and carbon dioxide. So we have to balance that. And then once we balance it, this is where the balanced equation conversion factor comes into play. It's a middle step. Every problem that involves a chemical reaction, no exceptions, has that middle step. And the first step is a simple conversion, grams to moles. The last step is going from moles to grams or whatever you're trying to calculate. Every single stoichiometry problem. So I'm going to give you a nice pattern to follow. So whenever it's stoichiometry, it's 3 steps. What's given, convert to moles. What's the mole ratio from the balanced equation? And then convert to what you're trying to calculate every single time. Now, I'm going to be giving you an alternate dry lab. All it is stoichiometry problems. And it's a whole page of them in small type with the answers. And with the answers comes a setup. So this is what I consider for this problem the setup. All that. So that's what we're going to cover on Monday. And this fancy word stoichiometry is just the mathematical relationship between the products and the reactants. I gave a test about 20 years ago, and I needed a 5-point question to make it 100 points. And the name of the test was stoichiometry tests. So it was on the second page. I said, what are we studying for this test? Right? Half the people missed that problem. I was giving you guys 5 points. It was fun. Funny if you created the test, not funny if you're taking it. But anyway, this is a big deal. This is a very big weakness on incoming students in 1A and 2A and 3A. Big weakness. So this again, this test 2 is going to be really important for your preparation for that next chemistry class. Okay, that's what I wanted to cover today. Yeah.
You say that or not been done up.
It is. Go to files. Tabulated. You will see it says dry lab 9 stoi. Stoi is short for stoichiometry.
Will that actually be an assignment that do, or is that just for like continuing?
That's in lieu of doing the lab 9 that's in your. And this will give you a lot more practice than that dry lab in the packet. You can just. Yeah.
We can just submit this in place of.
Right, exactly. And these are all the answers. So in fact, let's talk about these answers now. Remember I said stoichiometry problems are always in 3 parts, 3 conversions? Okay, so we've got, this is the I don't know if I can draw, I don't think I can draw on this. We've got, first step is we convert to moles. Middle step is we balance the equation. And then we look at canceling the CO2. So CO2 is going to be in the bottom. Then we look at the coefficient in front of the CO2, which is over here, 8. And what we're trying to calculate is on the top. But this comes from the balanced equation, this middle step. And then over here, we're converting to grams. So moles to grams. Every one of these, step 1, balanced equation, converting to what you're trying to calculate. Every single one of these. 3 parts. That's why I want you to do a bunch of these, so you'll know exactly how this pattern works out. So these story problems, word problems, are really breaking down the parts and strategies. It's not too bad. But if you don't have a strategy for working a word problem, they're hard. Every one of these, same thing. The only thing that might add an extra step in is if you started with kilograms, gotta convert to grams. Or at the back end, you need to convert to kilograms from grams. But again, every one of these, same thing. Convert to moles, ratio from the balance equation, convert to what you're trying to calculate. In this case, we're trying to calculate kilograms. So that's a harbinger of what's coming. So that's your dry lab substitution. So I'm going to give you a preview of a little extra credit problem. For extra credit, balance that. So who in here has had balancing equations before? Anyone? Okay, so if you had high school chemistry, you probably had balancing equations. I was when I was teaching high school up in Washington, I used to help out at the track meet with my buddy was a coach and he always needed helpers and stuff. So I was there just helping out. I was doing a long jump and one of the coaches from the school we were competing against was a chemistry teacher. I go, oh, and this is, track is spring sport. Spring, end of the year. I said, oh, what are you guys doing? Oh, we're just learning to balance equations. I covered that in the first month in high school. First month. This is like in April. I couldn't, so high school chemistry is like all over the place in terms of what they're doing and stuff. Anyway, this is an interesting problem. The reason why it's extra credit is because it's hard. So don't do this until we go through balancing equation practice. But it's hard. That's the reason it's extra credit. Okay? Yeah.
It just means putting the numbers of like how many molecules each so that the.
And yeah, right in the, well, can't write on this, but in the front. There's a number here, which if it's missing is 1. So right now it's 1, 1, 1, 1, 1. The other thing is when you're doing this, don't be afraid of big coefficients. The numbers in front are called coefficients, big ones. I'm talking like 3 digits big. 100, 200, whatever. That's where a lot of students get confused because when the coefficients get big, they start going, something must be wrong. But life is not that way. Sometimes it's complex. Anyway, extra credit. And is anyone in here had linear algebra? Okay, huh?
Okay.
Remember matrix? Remember reduced row echelon format? You can solve chemical equations using matrices via linear algebra. Well, most calculators, scientific calculators, have matrices math built in. So that equation I just showed you, the extra credit one, most students spend about 90 minutes balancing it. 32 seconds doing it on this. And that's how long it takes to set up the matricing. It's really wild. And if you've never had that before, matrices, it won't make any sense. But if you have had, if you want to try it, I have a worksheet on how to do it. I taught a chemistry class up in Washington for engineering students. And no one wanted to teach it. I said, oh, well, teach it. And what was cool about the class is I could throw whatever kind of math problem I wanted at them, and they've already had a ton of math. So it was a really kind of cool class. We just focused totally on chemistry, not how to do math problems. And they would use reduced row echelon format to balance all their equations. Because they, in their class on linear algebra, they use balancing equations as examples of how to use that process. It's kind of fun. So they would just throw everything into the matrices. It was kind of like the movie. Okay, so that's basic conversions of restored geometry. Okay, so we are done for today.